Hello and welcome to the final module in the probability of weather type precipitation type scenarios series. This is Dan Baumgart and I'll be taking you through this module. This is the fourth and final module on the use of the ProbIcePresent grid, or the grid that is the probability of ice present. It is ProbIcePresent in the PoWT and in GFE. Some basics about the ProbIcePresent grid. Why is the presence of cloud ice important? I think you've gone through the top-down training, so you obviously realize that in wintertime, cloud ice introduction is pretty important to the precipitation type process. It basically determines the importance and need to assess warm layers aloft, the cold layer near the surface, and really has an important big importance on precipitation type. For example, if you don't have any ice coming into a warm layer, then the warm layer assessment is meaningless. And so this is a nice example of that case there. Recall your ice nucleation temperatures here. Anything warmer than -7 in the ice nucleation regime is a 0% chance really of nucleation in that area. So you see -5 here in the sounding, and that is the minimum temperature, and there is no ice aloft in that -10 to 20 regime here. So you don't need to assess the warm layer. This is an all liquid layer here near the surface. So the ProbIcePresent grid really tries to target probably precipitating layers. Those are layers that we look at for the presence of ice that are greater than 1 kilometer deep, and they have a mean RH, or relative humidity, of greater than 85%. So the ProbIce really looks for those types of precipitating layers. If it doesn't find any of those layers in the sounding environment, in the model blend, or in the models themselves, it will assign a ProbIcePresent of 100%. That is the default value for ProbIcePresent. So in this scenario here, we do have a layer that's been found that would be found with the mean RH of 85%. You can see the relative humidity of this layer is about 100%, and it's well over 1 kilometer in depth. So you would trigger the ProbIcePresent here to look at this a little bit closer. So why did we choose mean RH of greater than 85% and greater than 1 kilometer deep? Well, we looked at some drizzle and freezing drizzle events to try and get some of the characteristic of those environments. So here's 110 freezing drizzle events that lasted over at least 3 hours at St. Cloud, Minnesota from 1973 to 1995. And what we've plotted here is the layer depth of the drizzle layer, or the saturated layer, and then the mean RH of that layer. And you can see quite a few of those drizzle events where you were getting liquid precipitation out of that saturated layer were both deeper than 1,000 meters and quite a bit higher than actually 85% relative humidity. So we used that as a threshold to determine the relative humidity and depth of the layer, to call it probably precipitating. As far as box and whiskers here, we've taken these dots and put them over into the box and whiskers. And you can see here, this is the 25 percentile. So 75% of the population lies above about 1,200 meters here, or 1.2 kilometers. Really, when you look at 1 kilometer, about 80% of the population is greater than 1 kilometer for these layers. And so that's what we arrived at to diagnose what these probably precipitating layers are. So then what we do is we look at that layer and simply look at ice nucleation temperatures and derive probabilities based on many aircraft reports, and you probably learned that in the top-down modules on the top-down precipitation type. But here is our curve that we use for the probability of weather type. So here's the minimum temperature in the layer along the bottom axis, and then the probability of ice present. And so that -7 to -15 is the most critical, because you're going from basically 0 to 100% ice present within that saturated layer. So when we look at the sounding over on the right-hand side with a minimum temperature somewhere around -5 Celsius, you can see that you lie on the 0 probability of ice present for this case. So kind of just a summary here to put it all together. As an example here, ProbIcePresent, if we have a saturated layer of greater than 1 kilometer, and for the next 3 scenarios, these are all saturated layers greater than 1 kilometer. If the minimum layer temperature is warmer than -7 Celsius, the ProbIcePresent will have a 0 value. If there's a saturated layer between -7 and about -15 Celsius, those values range anywhere from 1 to 99%, depending on how cold that layer minimum temperature is. And then once you arrive at -15 Celsius, you're at 100% probability of ice. And then one more note to make here: if the entire troposphere does not have a probably precipitating layer, it's going to be probably a dry situation, and the ProbIcePresent is assigned a 100 there too. And so really what we're targeting here for values that are less than 100 are these saturated layers that are warmer than -15 Celsius. These just so happen to correspond pretty well to drizzle and freezing drizzle environments. So let's just take this one sounding here for the first case. Does it have a probably precipitating layer of 1 kilometer deep with an RH of greater than 85? No, it does not. And so the ProbIcePresent is triggered into that dry troposphere, which is a 100% value. How about a secondary example here? We'll take and assess for a probability precipitating layer. And yes, this one does. The mean RH here is greater than 85%. You can see the depth is about 1.6 or 7 kilometers on this one. So ice nucleation temperatures, then we have to look at this layer and diagnose what the ice nucleation temperature is. The minimum temperature in the cloud layer is about -3. And so there the ProbIcePresent is assigned to 0. If you go back and remember that everything warmer than -7 Celsius is going to be assigned a 0 chance of ice ProbIcePresent, just simply based on the ice nucleation temperatures within that layer. It's unlikely you're going to see ice crystals form within that saturated layer. There is one final check that the ProbIcePresent code will accomplish, and that is it will look for, when ice layers are detected, it will look for dry layers below. And so therefore, in this scenario here, you see ice would be detected aloft in the -20 to 30 regime where it's fully saturated. But then we have this over 5,000 foot dry layer. And then we also have a saturated layer, which is a probably precipitating layer, down low, which is almost 1.5 kilometers deep. So basically, the code will look for dry layers of relative humidity over ice of less than 75% existing for greater than 5,000 feet. So in this case, it sees that. So what happens? The probability of ice present value will be ignored for that layer above the dry layer. So we have ice being formed in this layer here, but because of the dry layer, we ignore the ice that's formed here because we think it will all sublimate before it reaches the surface layer. So the surface ProbIcePresent, if you look at the minimum temperature there, is about -4. So we would get a ProbIcePresent value of 0. Aloft, we would have a probability of ice present of 100% because of the very cold temperatures in that layer. But the temperature, that layer aloft, is ignored because the ice sublimates. And so you're left with this ProbIcePresent of 0% for this probably precipitating layer near the surface. How about one last example here? Let's look at this again here. We have 2 layers. Significant here, again, we see this warm layer. Do we need to assess this warm layer? Is it important? So we have 2 layers, and so the upper layer, ProbIcePresent, is 100%. It's in that cold regime again. The lower layer, we see 0% near the surface because it's about -1 or -2. And so it sublimates in the middle portion of the sounding here. We see a big dry layer that's well over 5,000 feet deep, and so the lower layer is assigned that prob ice present of 0. Finally, let's go into example 4 here. Probably precipitating layers, yeah, not near the surface in this case, but up aloft we see this deeper ice layer. With respect to ice, this is going to be saturated. This is the dew point line, and this dew point depression is small enough so that when you look at the ice curve, it would be saturated. So we do have a saturation up high there, would mean relative humidity of greater than 85%. And the ice nucleation temperatures would obviously give this ice present a 100%. However, it does sublimate as it falls because of this very dry layer of 5,000 feet down below it. And so the layer above is ignored. And in this case, the prob ice present will be sent to 100% because of the dry environment that it's seeking. So kind of an interesting scenario here. We would have 100% ice here coming down, but it sublimates, but yet the value still ends up at 100 because it's a non-precipitating sounding. That way, we'll show you spatially, you can really get a sense for where these low-level liquid layers are. So the prob ice present grid basically is less than 100% for possible saturated liquid layers where the 1 kilometer depth is reached or greater and the temperature is warmer than minus 15 Celsius. So when the prob ice present is 0, it's a high probability of all liquid precipitation types, and the warm layer is not activated in that scenario. If it's somewhere around 50%, you've got an equal probability of all liquid and ice being activated. So we do activate the warm layer in this situation, but we mix the probability of types accordingly more to a 50-50 match of both all liquid outcomes and ice type coming into a warm layer that may be present. Okay, it's time for you to have a little bit of fun with a little bit of advanced learning. I'm going to give you a scenario and then I would like you to stop the video, think about it, and think about how you would answer the questions. And let me give you a little bit of a setup for this. First, we have a situation here. This is Wisconsin, Minnesota, Iowa, and we've got a cross section through the prob ice present grid. You notice values of 100 near A, and then we move into a regime in regime B here where the prob ice present drops to 0, and then the prob ice goes back up to 100 at C. So we're going to take a cross section through that area, and you see it right here. This is the relative humidity within that cross section, and then the temperatures. And you maybe can't see that clearly, but these are all below 0. So these are negative degrees Celsius for these layers. So I want you to think about each sector here, A, B, and C, and think about why the probability of ice is the value that you see here. So why is it 100% in A? Why does it trend over to 0% at B? And then why does it go back to 100% as you get closer to C? So stop the video, think about your answer, and then we will review it. Okay, so the answer for this is down across the bottom here. At point A, we basically have an environment that's too dry. The relative humidity is just too low here and not deep enough to call it a probably precipitating layer. And so what you end up with here is just too dry of an atmosphere and a value of 100. However, the moisture is deepening as we get towards point B, and it's deep enough to now trigger a probably precipitating layer. And when we assess this for ice, we see that our layer minimum temperature is somewhere around -6, which tells us that ice nucleation is highly unlikely, and so our probability of ice present is 0. Notice the gradient here as you move northeast, and then you get a similar gradient as your temperatures also cool and your layer deepens as you go towards C here. And by the time you arrive at C, you notice that we're very deep here, and we're actually saturated with high relative humidity, over 90%, all the way up to -19 Celsius. And so in that case, you'll have an ice nucleation occurring within that layer, and you simply have ice falling vertically and so the whole layer will be glaciated, and therefore your probability of ice is 100%. Let's move on to a few different scenarios here. This is a case from early January of 2017. We've got some observed soundings on the left-hand side, and on the right-hand side is the National Blend of Models beta test for version 3, which is putting out a ProbIcePresent grid. And so this is not a perfect, this is actually a blend of the models, a 1 hour forecast of the blend of models. And so it's a blend of about 8 models in the short term. So the soundings, just understand that this is sounding data and this is model data over on the right. However, we're going to go through and look at how close the national blend was with compared to a few soundings for this case. So here's Amarillo, Texas here. You notice that the saturated layer in the low levels tells us that it's a probably precipitating layer. We've got dry air aloft. The minimum temperature here is about -7 or so, and so we just barely touch on that ice nucleation temperature getting cold enough, and you notice that the probability of ice present here is 5. So that makes sense, right? This layer probably doesn't have ice in that layer. Let's move a little bit further east to Norman. At this time, freezing rain was being reported out of this sounding. And you notice this sounding has a minimum temperature about -5 Celsius, but it's very deep in its saturation, almost 3 kilometers deep in its liquid layer here, and the probability of ice present is 0. As we move further east yet, here's the Springfield sounding here, -5 or so looks like the probability or the ice nucleation temperature. We've got a probably precipitating layer of over 1 kilometer deep. It's well saturated, and -5 nucleation temperature would give us a ProbIcePresent somewhere around 0, and the ProbIcePresent in the National Blend of Models is 10. So there's different models that go into this, and so maybe one of the models had a sounding that was a little bit colder and pulled the ice nucleation temperature just up from 0. But you get the point here. All 3 of these soundings we've shown show that you have a deep liquid layer that could give you drizzle or freezing drizzle. And if the vertical motion is enough, then you'll get collision coalescence to form larger drops and go towards rain. And that, in fact, is what was happening. Here's just a shot from Iris. This is Missouri here. Here's the boot heel of Missouri. And then we have Kansas and Oklahoma. There was a band of freezing rain that stretched across all of southern Missouri back through the Norman area, or at least northeast of Norman and into southern Illinois. How about further north? What are these values of 100 that you see up here? Well, notice here both of these soundings are too dry to provide us with a probably precipitating layer. And so the same thing at Topeka here and Springfield both have values of 100 set because we don't have a probably precipitating layer. So let's go through a scenario here in the grids. We're going to look at just a scenario here with a dry punch moving in through this forecast area. We've got temperatures over the domain all below 32 Fahrenheit. And we're going to have an elevated warm layer come in aloft for this scenario, and it's a high chance that precipitation will occur from this case. Here's our QPF scenario. It's somewhere around 1 to 2/10 of an inch. If we just take a look at what the top-down grids look for this example we're showing here, we've frozen the max temperature aloft, or wet bulb temperature aloft through the day on Monday here. You see the warm layer aloft. We just wanted to keep a pretty easy to understand case, but you see the 4 degrees Celsius going to about 1 degree Celsius midway through the forecast area. So we move over to ProbIcePresent, and here I've built in the probability of ice present showing zeros making their way from southwest to northeast, something that you'd expect maybe from a dry punch as it scours out the upper level ice. And the prob of refreeze sleet in this case is going to be 0, just to keep it somewhat simple for us. So let's look now at what the probabilities of type look like, the conditional probabilities. Here's freezing rain. Notice the freezing rain, as we move through in time, is going to work its way northeastward. And I'm going to just put on the maximum wet bulb temperature aloft and turn this other debris off of our screen. So we start off with ice present in the morning. And notice the freezing rain is mainly contained to about 4 Celsius. But as the probability of ice present being 0 moves northeastward, we are now switching our precipitation type to an all liquid scenario. And so we'll see this more clearly in the probability of sleet. Here with ice present, we're using the warm layer, and then the eastern side of the forecast area, we lose ice, and so no longer are looking at the warm layer aloft. And this is the same thing for the probability of snow. As that ice nucleation is lost, as the scouring and the ProbIcePresent moves northeast, we lose our snow and go to an all liquid scenario. So notice here, here's the pot sleet and the pot freezing rain for this scenario. So in areas where that ProbIcePresent is going to 0, we are changing our forecast to an all liquid solution, either rain or freezing rain, where the warm layer does not have to be assessed. And there's our sleet amount back down where the max temperature aloft was, or the warm layer aloft was shown. So let's show an example of how you would handle a seed or feeder situation in the grids. Here we've got 2 layers. We've got a supercooled liquid water layer near the surface, and we've also got an ice layer aloft. So in this scenario, if we just looked at the first slide here, if we just pause it for a moment and move it back here, let's move it back to the first frame. In this scenario here, remember we're making ice here, but the ProbIcePresent looks for this dry layer, and so it sublimates any ice coming through that because it's 5,000 feet deep. And so the only thing that the ProbIce is going to pick up on is this supercooled liquid layer with ice nucleation temperatures not being in the activation range. We're at about -3 or 4 there, so it's going to be a liquid layer, and in this case a supercooled liquid layer. And then as we go through time, the ice starts to make its way into deeper saturation, and so the ice would at one point make it down to the feeder layer and glaciate all the supercooled liquid that's found in that layer there. So slowly the ice probability of ice present is increasing through this sounding every hour through these hourly this hourly time lapse. And so our ice probability of ice is increasing during that time frame. So let's look a little bit at what that would look like in the grids and how you would build that into the grids. We're going to have our same scenario where it's all below 0. And we've also frozen the different parameters like the max temperature aloft still the same scenario as we saw before. So let's look at the max temperature aloft here. And there it is again. All of the temperatures greater than 3 or 4 Celsius are across the south. Then you have this sleet band that would come in here if we were fully ice present, full deep saturated sounding. But here's our ice present. And so what we're going to do is take this area here over southwest Wisconsin and slowly increase the probability of ice present as that seeder feeder mechanism kicks in. So we start with values right near 0 in that area and increase to 100%. So let's look at the effect here. We start with freezing rain. And then with time, moving again with the ProbIcePresent, you see the probability of freezing rain here. Everywhere it's 0 starts at 100, and slowly we actually activate the warm layer aloft because we are building towards 100% ice probability. And so what happens is the warm layer aloft now is active, and we basically combine or confine our freezing rain area to that warm layer max wet bulb temperature of 4 degrees, 3.45 or 4 degrees or less. And then the sleet is the same, found just to the north of the freezing rain area in that 1 to 3 range. And then the snow, confined mostly to the ice area at first, will slowly make its way southward too during this interval as the ProbIcePresent increases. And again, let's look at the max wet bulb temperature aloft for the snow. You see all the snow is basically less than 1 Celsius. Now that we've got ice introduced, the sleet is in that 1 to 3 range, and the freezing rain is where we have a max wet bulb temperature aloft of over 3.5 to 4. So what about making snow amounts and ice accumulations for this scenario? I can't imagine doing this by hand, but the code knows how to do it, knows how to break up the QPF by the different types, and you get a pretty reasonable outcome for sleet, freezing rain, and snow accumulations. So as we come to the end of this module, just one more important note. When you're working in your top-down grids in the forecast builder, it's very important that you collaborate those top-down grids. You want those top-down grids looking well matched with your neighbors. Because we derive so many grids, the list here in the box, from the top-down grids and your base grids, it's important that those are collaborated first, because these are all derived grids. If you take care of the basic foundational grids, like the top-down grids in your basic temperature, dew point, wind, etc., all of these other grids will be collaborated as well. So this concludes that last module of working with precipitation types on the probability of ice present grid, and thanks for your attention.